Module 2, analysis of algorithm efficiencies and the brute force method. Yeah, 2 parts. Yeah. First, part A. Yeah, actually we have part A, B, C, D. Yeah. But today we cover part A and part B. Next time, part C and part D. Okay. Part A, problem solving from experience and elimination method. Yeah. 8.1, selection sort. So we will learn our first sort algorithm. Now, remember, at this point, we have learned one search algorithm, linear search, sequential search. Also, we learned one selection problem. Now here, selection sort, selection problem. That problem, finding the minimum. That's the selection problem. And here, our first sorting algorithm, but its name is called selection sort. Okay, all right, so let's start. Our problem number 5, sort an array. First, let me give you the question, given an array. Yeah. The question, how to sort it in ascending order. Yeah. I hear some noise. Yeah, so this is the general question, and in this class, we will solve the same problem at least 6 times. That means we will have 6 different sorting algorithms. This is the first one. At least 6. Could be more than that. Yeah. All right. The problem type, sort. Yeah. 3 basic problem types. Search type, selection type, now sort type. Yeah. All right. I'll give you the reference in the textbook. Yeah. All right. Let's do analysis. Yeah. Remember the title, learning from the experience. When we need to solve this problem, we need to recall some related experience we have. Related experience. Yeah. All right. So that's module 1. Module 1 is our experience, our background knowledge. Okay. Yeah. Find a solution from our experience. So here you can see experience is important. Yeah. So we try to, expand our experience. If we have a lot of experience, then our problem solving skills could be better and better. Yeah. All right. Explore the properties. Yeah. So another step we commonly use, explore the properties. When we look at the whole problem, we need to study from different angles, and we try to discover many special properties. Here, given an array, we want to sort it in ascending order. You have many different angles you can look at this question. Yeah. Here, we try to explore some special property. Yeah. Okay. All right. So that's because these 2 things are very general, right? Not for this particular problem, for general problem. So our guidelines. All right. And here we also use backward thinking. Another commonly used problem solving method, backward thinking. Okay. Yeah. So we assume, so what's the backward thinking? We assume we already have the whole array sorted. So then we do the, logical reasoning backward. Yeah. So that's another commonly used method. Here, let's try this way. Yeah. Question, if the array is sorted, what problem can we discover? Yeah, so we look at it in this way. We assume the array already sorted in ascending order. Okay, yeah. Here, for simplicity, we can assume distinct elements for convenience. In real way, we cannot make this assumption. But in our solution, think about we can make our life easier. We can make appropriate assumption to make our life easier, right? Question.
So is the backwards thinking then like we're starting with the simplest possible like answer?
All right, so here it's different. Yeah, this different. Simplest. Yeah, when we get there, when we have a complicated situation, then we need to start with the simplest.
Okay.
Yeah. Here we haven't. Yeah, because here we try to discover some property. See, we want to look at the whole picture. If you look at the simplest case, one or two elements, then you do not have a global view. Your view is too narrow. Think about it. Suppose you only have two elements in this array. Although it's simple, but your view too narrow. You cannot discover property. Yeah, the property, not that obvious. When you have two elements, the property is not that obvious. So you don't want to simplify it. Yeah, here. It's a good question. Yeah. Sometimes we want to have a global view. Yeah, we don't want to make it very simple. There a lot of information missing. We couldn't discover. Yeah.
For something like this, like would an example of a property be the minimum, like the whatever element is the smallest?
Yeah.
It's going to be at position 0. Is that like considered a property of this? Like
Yeah.
for this specific problem?
Yes. Yeah, that's a property. Yeah. So yeah, pretty close to what you said. Yeah. All right. Question: how to connect this problem to the minimum problem? Yeah. Minimum problem. That's our experience. You know the minimum problem well. You know how to find the minimum problem. Okay? Everyone here knows how to find minimum problem. So you can use that solution as the starting point. That's our starting point. Okay? Yeah. All right. Then do the critical observation. You need to find the main property, critical observation here. Now, what's that? Look at it. So this ascending array in ascending order. Okay. How do you connect? Right now, this is the result. Backward thinking. That's the destination, the final state of the sorting. Okay. But can you connect this to our minimum problem? Then old solution can be used here. So that's the reason we want to connect. When you see that ascending order sequence, can you say something about the minimum problem solution? When you see the sequence, don't get into that detail. Yeah, the MSO comparisons, that detail we need it, but here, don't worry about that. Yeah, because we know, think about, you know the whole solution. You know the whole solution. So you don't worry about how to find it. Okay? You assume you can always find the minimum element for any array. Okay, so you have it. Then the question, the property, how do you connect minimum problem solution with our final state of the sorting problem? Relationship, yeah. Observation, yeah.
That each
Yeah.
step in the element is going to be the minimum subtracting the previous element.
Yeah, great. Yeah, simple, but that's the point. You get to the point. Okay.
Say that again.
So then if you have the array right here and you've identified the minimum element, if you remove that from the array and perform the minimum problem again, you're able to find successively each element in order.
Yeah, exactly. But I will, expand your description as a whole story. Yeah, and go through. So don't worry. Yeah. So because it's a big story here. All right. Now, here you can see the observation is very important. Yeah. So when you look at it, based on your understanding, so you make that critical observation. All right. That is A0 is the minimum of the whole array. A0. What's the A0? The first element in sorted array. That's A0. The first element. That's the same as the solution of the minimum problem. Okay? That's our observation. That's the critical property here. So we will take advantage of this property to complete the whole sorting algorithm. How about that? Think about it. Huh? Yeah, so let's do that. All right. The concept here, before we complete the whole story, I like to use this in place concept. Actually, the meaning, easily. Here we say in this algorithm, matching your understanding in real world experience. All right, here we know when A0 is the minimum of the whole array, we should put it in the first position in our destination array. Okay, and that position is the right one, right? Correct one in the sorted array. So that position, right one, so we call that element is in place. We put it in place. Okay, that's just terminology. So later we're going to explain. Yeah. All right. Here with this concept, can we say this? Given an array, original array, can we apply our minimum problem solution on the original array? Yeah, we can apply, we will get a solution, right? And here you use that A-1 comparison. Here you use that detail put here. Okay, all right. After we get that solution, can we put it in place? In the destination array, we just grab that solution and put it in place. How about that? And after that, because one element is already in place, we do not need to worry about this first element anymore, right? In the remaining processing, we can ignore the first element. How about that? Yeah. So then, for the remaining elements, can we apply the minimum solution another time? We find the second smallest, and so on. In this way, can we solve the whole array? Yeah, so you get it. All right. So that's the definition. The element is placed at the position when the array is sorted. Yeah, array is sorted. So there is a ascending order. That order, okay? In that ordered array, that position, if the array is at the same position of that place, it's in place. Okay, yeah. Now you can see the connection. Then now you can understand why we call the sorting algorithm selection sort. Because the main operation we apply here, the selection problem. Minimum problem is a special selection problem. Okay? So the solution of this sort is based on a solution of this special selection problem. So we call it selection sort. Okay, yeah. All right. And here we also use the elimination method. Although it's a simple version, yeah, but another time we use elimination method because after we put the first element in place, we can eliminate from consideration. The second round, we do not need to consider A0 anymore. We eliminate it. Okay? In that way, we reduce the problem size. The problem size get smaller, smaller and smaller. Then after we reduce to the last element, trigger. Trigger. Nothing to do. Question? Yeah.
I was just gonna make some comment about how
Yeah.
long it would take.
Yeah, good. That's our next step.
Yeah.
How long? Because we need to consider the efficiency. Yes, won't be good. Yeah, won't be good. Yeah, this solution actually we can treat as the worst of
Yeah.
all we have. It's the worst. All right. Yeah. So, and yeah. So in each round, we place one element in place. We guarantee. Yeah. Every time we scan the remaining elements, we guarantee we can place one element in place. How about that? Yep. Yep. Think about until we put all elements in place, the whole array is sorted. All the elements in place, the array is sorted. But the last element, we don't need to do anything, right? When you have last element, you just put it right in place. Put it at the end. The last one then. The last position in the sorted array. Yeah. All right. Then now, so question. Yeah, here, actually, we already have that. Yeah, here, I just run this diagram to, to show the procedure. So the first time we find the minimum of the whole array, so we put that element in place. Okay. Then the second round, we only consider the remaining elements, ignore the first one, then we find another minimum element, we put it in place, and so on. Okay. Now, the last one, we don't need to do anything, we just put it in place directly. Okay. Now, so that's the whole procedure. Yeah. Conclusion. Now, yeah, so the first simple fact, right? That's a simple fact. When all the elements in an array are in place, this array is sorted. The simple fact. Okay. Yeah. But I like to, put it there to bring your attention. Yeah. Because later we may need to use this simple fact answer other questions. Yeah. All right. Efficiency analysis. Let's count the number of comparisons we need. The number of comparisons we need for this sort algorithm, for the best case, for the worst case, and for the average case. Let's answer this question. Okay, yeah. All right. Let's count the number of comparisons. The first round, n-1, backward, right? Backward. n-1, n-2, the last one is 1. Number of comparisons. Okay. Adding up, so the final expression for the number of comparisons is this number for the whole algorithm. Now, tell me, what is the best case efficiency? What is the worst case efficiency?
Best case be that it's incidentally in order already, so every sort is just one comparison. That would be like our best case, or between sorts.
Anything? Say anything?
The worst case be descending order?
All right.
But
Right,
it could be like n
Alright.
elements like is.
Yeah,
or n
it's possible.
for
I-
changing n.
It's possible.
But aren't we already comparing every single one? So
Right, every single one.
we don't have, our best
Oh,
case
yeah.
and our worst case, aren't they the same?
Same, yeah, that's the answer. Because even ascending order descent, you need to compare with everyone. When you find the minimum, can you ignore any of them? Yeah, when you find the minimum, although the first one is the minimum, but if you do not check all the remaining elements, how do you know there is a possibility some element at later position could be smaller? You don't know. So you have to do all the comparisons. Yeah. So the best case, worst case, the same, then average case also the same, because you only have one case, right? Then you do average on one case, same thing. Yeah. So for this algorithm, we only have one case. Yeah, so the answer, the same thing, same number. Okay, yeah, all right. And here, I like to do a small summary on that elimination method. Because later, you need to apply this elimination method on several challenging questions. Now, actually, this week, next week, our third week, after next week, you need to have your first homework assignment. And then you will have a few challenging questions. Some of them we need to use elimination method. Okay, all right. The goal, reduce the problem size. When we do elimination, we reduce the problem size and make it easier. Okay, yeah. So the smaller the problem size, the easier the problem. That's the general fact. May not be always true. Sometimes there is exception. Sometimes the smaller size could be harder than larger size. That's possible. Yeah. Yeah. Because later, when you here, I can give you an example. Prime factorization. Okay. If you do prime factorization on some number n, the n value we treat as the problem size. N value, magnitude. Yeah. Suppose we consider n value 1,000, it's larger. Okay. When we compare with 357, which one easier to do factorization? Okay, the larger size could be easier, right? And the smaller one, prime factor, you need to, do some work. Okay, yeah. But this principle in general, correct, but always some exception. Okay, yeah. All right. When some elements do not change the outcome, yeah. If we know after we do some work, we find certain elements cannot affect the final outcome, so we can comfortably eliminate them from the configuration. But if you are not aware of this, you still keep those, useless elements. We could say useless element in the group. Then you may do redundant operation. If you put useless elements there, you may put some redundant operation. You waste your operations. Okay. Yeah. All right. So that's the this method summary. Yeah. Next topic, 8.2, impact of organized data. When we pay some cost to organize our data, there is a cost you need to pay. Yeah. You need to look at the benefit. Is the benefit big enough to cover your costs? Okay, yeah, to make your investment worth of it. Okay, all right, so let's look at our question number 6. Element uniqueness problem. Element uniqueness problem. From the name, you can guess the meaning. So given an array, yeah, how to check if all the elements are distinct. That's simple. But you want to find the fastest algorithm to check it. You can do it. Everyone can do it. But think about, is your algorithm the best? Can you do faster? Right? Yeah. Yeah. So let's use 2 different methods. Then we compare. Okay. All right. The first one, brute force method. Brute force. So here, the brute force, so we mean you do not apply any technique. So you just work on it directly without any special technique. Okay, brute force. Yeah. All right, yeah. So do nothing to organize data. We don't do anything. We just do comparisons directly and check if we can find there are 2 elements in the array, they have the same value or not. We do all the possible comparisons. You may need to do all the possible comparisons. Yeah. All right. Here, the data organization part are no cost. So you work on it directly. So you do not do anything to organize your data. Yeah, so no cost in the first step. Okay, yeah. All right, so now let's look at the comparisons. All right. First, in the first round, we want to see if the first element appears anywhere in the remaining elements, happen to have the same value in the with any of the remaining elements. Okay, got it. You need to do n-1 comparisons, right? The first one, you need to compare it with all the remaining n-1 elements. So n-1 comparisons for the worst case, right? For the best case, you only compare with the first one. They happen to be the same. Then you have the answer. Yeah. Because uniqueness, no, the answer is no. The first element equals the second element. The answer is no. Not unique. Not unique. Okay? Yeah. For the worst case, you need to do n-1 comparisons. Okay? Still not enough. The next round, the second element, you need to do comparison with all the remaining elements with n-2 comparisons. The worst case, still, you cannot find a match, still different values. So then you consider the next one by one, until the second to last one, you do one comparison, still, yes or no, it doesn't matter, but you have done all the possible comparisons. That's the total number of comparisons. But for the worst case, okay, yeah. Yeah, the last one, yeah, so you do not need to do comparisons. So we can calculate, we can do the analysis of efficiency. We just count the number of comparisons. Best case, this situation, all right? Yeah, one, yeah. One comparison, the best case, okay? Worst case efficiency, yeah. Yeah, so that's an example, okay? One of the examples, you have many different examples. One of the examples, that's the total number of comparisons. Okay, best case, worst case. Yeah. Here, the question, how to calculate the average case? Think about it. How to calculate the average case. Okay, yeah, not that easy, right? Your average case, because you need to consider all the possible cases. Then you do the average. Can you exhaust all the possible cases? Right? Yeah. Think about that. Probability. Yeah. So what kind of probability assumption you can make? Yeah. Right. Yeah. Oh yeah, the probability. Yeah. So you can think it this way. Yeah. Because two possibilities you consider, unique elements and non-unique elements. Between these two groups, there is a possible probability, right? So uniqueness, what's the probability? Unique. Non-unique, what's the probability? Yeah, you need that probability. Good. Yeah. Here, I do not give you that question. You just think about it. Okay. All right. Yeah. So the average case, a little harder. Yeah. Just think about it. Yeah. Yeah. You can try. Yeah. All right. Next, we want to, that's our method number one, right? Now we do a different method. Method number two. Yeah. Pay for some cost to organize data. So let's do some data organization at the beginning. We try to make our data well organized. Then we may take advantage of organize the data. Okay, now let's do our method two in this way. Okay, investment in data structure. Here, yeah, we do some investment here. So we sort the array first with certain cost. We sort it. Now, before we check uniqueness, let's sort a whole array. We know it's costly. It has some relatively big cost. And we want to see if it's worth it or not. Worth the sorting extra work. Okay, yeah. But here we do not use our selection sort, yeah, but that is very slow. Yeah. Here we try to use some good sorting algorithm, and here I just give you this, the general performance we have for a good sorting algorithm, n log n comparisons. Close to this number, may not be exact, but very close. N log n. Yeah. Question? Yeah.
Do you know what the sorting algorithm we just talked about, efficiency was?
Yeah, actually, there are several. Yeah, we can. One commonly used quicksort. Quicksort has this efficiency, but for average efficiency.
But what was the one we just did with the minimums? Do you know how efficient that one was?
Minimum?
Yeah, the one we did, that we were talking about with the minimum values.
Oh yeah, selection sort, right?
Yeah.
Yeah.
What was
That's 2 squared.
Oh.
Yeah, yeah. Here we ignore some small number. Yeah.
Yeah.
But here we can see the dominant term. The dominant term is that.
Yeah, that's,
Yeah.
that's big.
Yeah, yeah. So yeah, the difference. Yeah.
Okay.
All right. All right. So the first step, we do the sorting, and we pay. The cost is pretty big. But if it's smaller than method one, probably we like to pay this much. Okay, all right. So that's yeah. Let's look at the next step. Yeah. Next step, how to check if any element is repeated in an ordered array. This time we have ordered array. Much better, right? Yeah. When we do the uniqueness check, now we can apply our comparisons on an ordered array. That's a big difference. That's a big difference. Right? Yeah. Why is a big difference in increasing order? Think about it. If you have two elements in the array with the same value, what property do you have?
They're gonna be right next to each other.
Yes. This time, you only need to do adjacent comparisons. You only need to do adjacent comparisons, all right? Because if there are two elements with the same value, you will find two adjacent elements with the same value. Because it's ordered. The whole array is ordered. Okay? Yep. Adjacent comparison, we can treat it as local comparison. Local, very local. In the first method, we need to do global comparison. Okay? That's very global. The first one with the last one. Very global. Right? So you, with this organized data, you do the sorting, you make the global comparison to local comparison. That's the big change. And how many comparisons do you need for this local comparison? Only compare two adjacent elements. Only two adjacent elements. Every time, two adjacent elements. How many comparisons do you need to do?
Wouldn't it still be n minus one? Well, oh, it's n minus one.
Yes, n minus one, not n minus one. Okay, two adjacent pairs, right?
That's
Two
one
adjacent
time.
pairs. Yeah, n minus one. Yeah. Good. Yeah. You can write a code, very simple code. Yeah. You only check, compare two adjacent values. Okay. If they have the same value, return false. Return false. False means not unique, right? The whole array does not have unique values. Otherwise, if you do all the check, you couldn't find two adjacent values the same, return true. Return true unique. Whole array is unique. Okay? Yeah. Now we need to compare these two methods. So our last step, we need to compare these two methods. And this one we need n minus one comparisons. Yeah. All right. So next step, we move to part B. We will have a new concept called growth functions. So here, we introduce this growth functions concept. Okay, yeah, all right. We use our part A example, yeah, formula between running time and the number of basic operations. Yeah. So here, I like to introduce the concept first. Then we apply this concept in our previous example. Okay, yeah. So the concept is we want to look at a formula between running time. Running time function, yeah, there is a function to calculate the running time. And there is another function, that's the number of basic operations, two different functions. And we want to look at the relationship between those two functions. Yeah, here. Notations. Yeah. Function of the running time, capital T of n. Yeah. Suppose, given a problem with data size n, we have some algorithm, we just clock it. We clock its response time. And the value, we use this function, capital T of n, to represent the running time function. Okay, yeah. Then we use another function that gives us the number of basic operations used. Basic operation for different problems could be different. Could be addition, could be multiplication, and it could be comparisons. Yeah. For this class, most of the time we use comparisons. Yeah. All right, yeah. So the operation, yeah, here, yeah, you may wonder, how do you define basic operations, right? We have additions, we have multiplication, we have two different operations. In that polynomial evaluation problem, multiplication is the basic operation. Addition is not, because multiplication has this property. The operation contributing the most to the total running time. Multiplication, that's the big part. Addition, very little, small portion. Dominant. Multiplication dominates addition. So we make that kind of operation basic operation. All right. Execution time of a basic part. So here we also need a quantity, one constant now. Oh, question.
Yeah, about basic operations. So if you didn't have multiplication in the function, would addition become the basic operation, or it's?
We need to, yeah, so here the question, we need to look at all the operations and we want to see which one contributes the most to the running time. Okay, yeah. So yeah, actually, so in your code, in your algorithm, you have algorithm first. In your algorithm, you look at for loop. Usually, you look at for loop.
Yeah.
For example, you have nested for loops.
Yeah.
Outer for loop, inner for loop. The operation that appears in the inner for loop, that one contribute more.
Okay.
Outer, because you do not get into the inner. When you get a nested for loop, you will apply that operation much more.
So
yeah,
with that being said, addition could be the
could
basic
be.
operation?
Definitely could be.
Okay.
Yeah, could be. All right. Yeah. In order to compare these two functions, so we need to use another quantity, little c up. It's a constant. It's constant. That's the execution time for one basic operation. But for different machines, this constant could be different. Usually it's different. But here we just assume there is one constant for one particular machine. Okay, yeah. So then we can compare these two functions. But we take approximation approach. They may not be exactly the same, approximately equal. So TON is approximately equal to C of times capital C of n function. Yep. a straightforward relationship. This is a constant, machine-dependent constant. Now, if you change the machine, this constant will be different, machine-dependent constant. Okay, yeah, all right. Well, you can see these two functions are proportional. The relationship, proportional. Okay, yeah. All right, yeah. And we know from previous classes, we know if we use the C function to measure the efficiency, it's more stable than T function, right? T function for different machines, so you have a problem. But for C function, for different machines, you have the same C function. Okay, more stable. Number of basic operations, the same. All right. So then we want to see what details we can ignore in our study, in our algorithm efficiency study. What kind of details we can ignore? Okay, yeah, so we want to consider that. Can we ignore some constants? In our formula expressions, we may have a lot of constants. Okay, if we carry all the constants, we can make our formulas relatively complicated. So we want to simplify our formulas. How do we simplify our formulas? Ignore some unnecessary or not important constants, that are not very important, that we can ignore. So here, let's look at this question. Can we ignore some minor terms? So here, let's do this ratio. Take the ratio, T of 2n over T of n. Look at this ratio. Because this ratio can tell us how fast this function increases. Every time you double the problem size, what is that ratio? Okay? If you have that number, so you have an idea how fast it increases. Every time you double the problem size. Okay? And for that ratio, when you use this approximation formula, this constant can be canceled out, equals this C function ratio, C of 2n over C of n. Same ratio. When you switch from T version to C version, this ratio, same. Ratio the same. And you know this ratio can give us information how fast the function increases. So you can get that, but so that tells us this constant is not that important. This little c constant, because we cancel out. Without that constant, we can also see how fast the function increases using the ratio. Okay, this kind of ratio. Yeah. That means this constant can be ignored if we want to see how fast, if we want to get an idea how fast that efficiency function. We use the function to represent efficiency, that efficiency function. That constant not important. Yeah. All right, so that's one observation from this equation. Yeah, so whenever we double the input, what is that ratio? If the ratio number is high, then the increasing rate is high. Okay. All right. So then, now we want to define this growth function concept. Growth function. All right. what is the major term in an efficiency function? Major term. We have many terms, major, minor, the major terms. I need to control the time, yeah. Because that clock, that direction is not good. Hard for me to see it, so I need to use my cell phone. See the time. All right. Major term, minor terms, we need to see that, yeah. And last time we saw this concept, dominant term. Dominant term. Okay, one term, leading term. There is one term. Value is much higher than those of all other terms. Yeah. So let's record the selection sort. In the selection sort, this is the efficiency function number of comparisons. C of n, this is our C of n. Okay, yeah. Let's expand that function. We have two terms. Okay, two terms. Can we say the first term dominates the second term in its value? We look at the value, it dominates. Okay, yeah. So it's the major term, the minor. Okay. Here, because after we identify major terms, minor terms, we can ignore all the minor terms. So we want to simplify. We only keep the dominant term. Okay. Because if you look at the percentage, the percentage of the dominant term could be much higher than 99-something%, right? If you look at the percentage, when n is sufficiently large, the percent of the first term much higher than 99-something%. So that's the reason you can ignore that minor term. Because less than 0 point many zeros 1%. The n is large. Because we only worry about large n. Think about it. The last time I said we only work in our algorithm efficiency study. We only worry about large n, very large n. For relatively small n, we don't worry about it. Okay? Our computer is very fast. But for large n, it could be very slow. All right. So that's what. So the first term dominates all other remaining terms, so we can ignore those minor terms. Yeah. So you do not lose much. Okay, yeah. Right. So that's the first concept, dominant term concept. Okay, all right. Then we move from dominant term to that growth function. Another step. There is another step. We try to simplify it. Okay? Because here there is a 1/2 constant here. Okay? 1/2 constant here. In our dominant term, we cannot ignore that 1/2 constant term. This dominant term. Right? But when we move to the growth function, we don't need that constant. We can simplify furthermore. For the growth function, why we need this constant? Remember in the previous slide, that little c of constant cancel out. It's not important. That constant. When we look at the ratio, it's not important. Here, if we do ratio, double the size over that constant is gone. Okay? Yeah. So when we consider the growth function, we can simplify this dominant term another step. Okay? Ignore that one, constant 1/2. Only keep the n squared, because that's the most important one. That's our growth function. The growth function definition is that. Okay? So, all right, so here, yeah. But here I just want to explain why the first term dominates the second one. Okay, using the limit way. Calculus. In calculus, you know how to calculate the limit. Yeah. Here, why I explain why the first term dominates the second one. We take the ratio, first term, second term ratio, when n goes to infinity. Let's find the limit. After simplification, this limit is infinity. Infinity, so you compare percentage, the first one, infinity, can be very close to 1. The percentage very close to 100%, right? A little smaller than 100, but very close to 100%. So you can comfortably ignore that minor term. Percentage is too small, okay? All right. So this formula, we just want to say that. Yeah. Why dominant? Why you say dominant? Okay, all right. Now, simplification. Yeah. Another step, simplification from dominant term to growth function. N squared is the growth function, right? Yeah. So we define growth function of this algorithm, selection sort algorithm is N squared. N squared. Okay? Yeah. So here you can see we only keep the most important part. For relatively less important numbers, we can ignore. Okay? To make our growth function as simple as possible. Because later, yeah, here you may ask me why we use this growth function concept. Why we use this growth function concept? Here, simple answer is this. When we compare two different algorithms, we only need to compare their corresponding growth functions. Okay? Yeah. That's enough. We only compare their growth functions. Which algorithm has larger growth function, then this algorithm will be slower, right? Because larger, you need to use more basic operations. It will be slower than the algorithm with fewer number of basic operations. That's the reason that we need to use this concept, growth function concept. Okay, all right. Yeah. So next, let's compare growth functions. In our part A, we did that element uniqueness. We find a solution, element uniqueness problem. We have method 1, method 2. Let's find the growth function for method 1 and the growth function for method 2, and we do comparison of these two growth functions. Then we can make our conclusion which method is better. Method 1 is better or method 2 is better. Yep. That's the reason we need this concept. Okay. Yep. All right, so let's do the work, compare two growth functions. Which method is better, method 1, method 2? We need to get the growth function. Method 1, growth function n squared, right? Method 2, we do 2 steps. Step 1, n log n. Step 2, n minus 1. The dominant term is n log n. The growth function also n log n. Okay? Growth function of the first method, n squared. Growth function of the second method, n log n. So now we only need to compare n squared with n log n. How about that? Okay? Yeah. When we do comparison, the limit way. Yeah. So we just did in the previous slide, the limit way. So let's do the limit. Calculate the limit of the ratio of these two growth functions. For the comparison. Use ratio to compare two growth functions. Right, yeah. The limit n squared over n log n when n goes to infinity. The ratio. Okay? Yeah. Simplify. Find this. Let's do cancellation. N over log n when n goes to infinity. calculus, here we need to use the knowledge of calculus. Knowledge. What's the log base? So here you can assume some reasonable log base. Some reasonable log base. What's the reasonable? Log base A, this A should be a number greater than 1. That's our reasonable log base. Okay? Greater than 1. If less than 1, it's negative. If A is less than 1, this log function is a negative value. So our growth function cannot be negative function. The number of basic operation always positive. Always positive. So we don't consider the negative case. So we assume A greater than 1. Okay? So this function is a positive function. We compare the ratio when n goes to infinity. Here, how to do the comparison. Let me check how much time do I have. Yeah, all right, I still have a few minutes. All right, the answer is infinity. Can you see that? The answer infinity, n over log n, answer infinity. So we need some knowledge to see it. We need some knowledge to see it. Here, how to see it? I'll show you some ways to see it. Method 1, variable substitution. Because log, usually we're not familiar with log, right? But log is always, so most people, most of our students feel it's hard to handle log functions. If it's hard to handle log function, can we use a new variable to substitute the old log function? That log is gone. After that substitution, the whole log function is gone. So we do not need to deal with log. Okay? So that's one way to avoid it. That little u equals that log base A of n. We introduce a new variable, little u, to get around log function. Okay? After we introduce this function, then we can represent n as exponential function with a base, a to the u exponential function. Okay? Yeah. All right, so n equals, let's go back to the ratio. After variable substitution, we will have numerator a to the u over denominator just the u. And u also goes to infinity. Because when your n goes to infinity, u also goes to infinity. Okay? Yeah. This time, you do not have log function. Okay? You don't have the log function. But what do you have? You have exponential function in the numerator and just a linear function at the denominator. Now, can you see when u goes to infinity, this ratio goes to infinity? Can you see that? Because we know exponential function dominates any polynomial, right? Do you know? Exponential function always dominates any polynomial. This is a special polynomial. Okay? Special polynomial. This is exponential function. Exponential function and exponential function dominates any polynomial. Yeah. That's our, real life experience. Yeah. But we can prove it. If you still you do not feel comfortable to accept this fact, okay, we can prove it. In our next class, I will show rigorously, we use rigorous math to prove it. Yeah, we will do that. Next class. Okay, part C and part D. We will do the proof. Yeah. Question? Yeah.
Is then that the math that proves this very important to know? Or is it just like a good concept to see written out?
The method is important.
Math.
Yeah, the math, because the math not just prove this special example, we need to use to work on many other examples. Yeah, but for this class, I may not require that much math. Okay, yeah, I show you how to do, yeah, but you just know it. Yeah. In my questions, I may not give you such problems, such questions, but good to know
Yeah.
those things, techniques.
I like showing things.
Yeah. But for the questions, we mainly focus on computer science questions. Not a little, small portion math questions, yeah, but should not be too much. All right, so let me come look at the time. Time thing 42, yeah, so, but let me see my next topic, yeah. This L'Hopital's rule, yeah, this L'Hopital's rule. All right, so actually, this tells you how to prove. This is cap 2.